Network Concepts 101, the OSI reference model versus TCP IP. Wouldn't it be nice if when someone came up to us and they asked us, hey, can you tell me how the network operates? Wouldn't it be nice for you and me to be able to communicate that and tell the person exactly how it works? Well, that's really what this nugget's all about, is to describe and understand the logical process that happens when one computer on a network wants to communicate with another device on a network. So we're going to take a look at these concepts of the OSI model and the TCP/IP protocol suite. Let's break those down. Every time we talk about a new term, I'm going to describe it with you. So OSI stands for the Open System Interconnect. That's the OSI model. It's a logical way of representing what goes on in the mind of a computer when it wants to communicate with another device on the network. Now, in the world today that we live in, the OSI is a terrific reference so we can understand and tell the story about how networks operate. But what we use in production is something called TCP/IP, which stands for the Transmission Control Protocol / Internet Protocol. Sometimes we call it IP or just Internet Protocol. But what this really represents, TCP/IP, it's a suite of protocols, a bunch of rules that operate together. Now, when somebody says the word protocol, let's talk about that for a moment. Protocol. When they talk about protocol, that simply means an agreement. If you and I come up with a secret handshake and we understand it, we can communicate in code, that could be considered a protocol to use between the two of us that we could both understand. Well, as long as two computers speak the same protocols or rules, which is what I'd like you to think of whenever you see the word protocol, they can communicate together. So TCP/IP is a set of rules that work together to allow a computer to communicate on a network. So we're going to start off our discussion with what exactly is the reason for a model. And the reason right now, right here, is simply to understand the process, to understand how the network functions. So that's the purpose for it. We're going to take a look at each of the layers of the model. Now, when somebody talks about layers of a model, let's say that you have a company and it has a very organized structure to it. For example, here's the president and here's the executive vice president, and you've got a manager and you've got a worker, and they want something to happen. Well, maybe the president talks to the executive vice president vice president talks to the manager talks to the worker, and then as stuff goes up, is completed, the worker tells the manager tells the executive vice president, and the executive vice president tells the president. So the reason we call them a protocol suite or a stack is because these protocols all work together, very similar to like this company org chart I just put in, where the worker talks to the manager and the manager talks to the executive vice president. But you notice the worker bee doesn't go straight to the president. There's a set of rules or protocol that are involved. So we're going to identify the layers of our protocol stacks and also the functions of each layer, what they do. We'll also identify the names. Now, why is this important? This is really important. As we talk about network functionality, we're going to use some terms that come up all the time, like, oh, hey, Bob, that's a layer 3 device, or that's a packet, or that's a frame on the network. Having a really solid foundation of understanding exactly what we're talking about when we say frame or packet is critical to your further learning. So we're going to spend some time in this nugget as well identifying the names for the data at each of the various layers of a given protocol stack. And then finally, I'm concerned that you completely get what each level does. For example, if we went to the manager and said, hey, Mr. Manager, I want to know exactly what you do as part of this organization, hopefully he could tell us. Now, in a protocol stack on a computer network, you and I, definitely want to make sure we understand each and every component of what each layer does. So without further ado, I'd like to tell you a story that's going to knock out of the park the concept of the OSI reference model by giving you a story that you can repeat and share with others. And after you understand this story, you too can explain how a network operates. Let's jump in. So the objective of this discussion that you and I are having is to understand the OSI model. And I want to put that off to the side just for a moment. And I'm going to walk you through the story of how a kingdom operates. And you might be saying, Keith, a kingdom? Really? Like with King A? Why? Well, if we understand this story that we're going to go through together, we can apply virtually everything from it to how a computer and a computer network operates. So let's start off with a King A at the top of the stack here. And what does a king do for a living? Well, he does pretty much anything he wants. He has some responsibilities, that's true, but he's the king, the top of the hill, the best of the best. He's way up there. And if King A wanted to invite someone to lunch, for example, maybe he wants to send an invitation to King B. Maybe King B is way over here. He wants to invite him to lunch. Do you suppose King A has to get up off of his throne, go out and run across the countryside or ride a horse and deliver the invitation to King B himself? Yes or no? What do you think? Well, because the king is at the top of the stack and everybody works for him, the answer is no, Keith. He doesn't have to go out himself. He's got everybody in the kingdom working for him. So what does he do? Well, if he wants to send a message to King B, what King A will do, he'll call for his scribe and he will verbally give the scribe a message, which the scribe then writes down. So the scribe, as he writes this down and says, "Dear Mr. King B, I'd like to have lunch. Signed, King A." And the scribe is adding a little bit. I'm going to say 2 cents. The scribe's adding his 2 cents. Now that 2 cents refers to he's adding a little bit of extra information. For example, maybe there's a period or a capital letter or parentheses and so forth. But as the scribe writes it down, he's adding a little bit of overhead to the message. Now, what happens next? Well, this scribe, he's got a great job. He's way up there in the political hierarchy. Does he have to get out on a horse in the early morning and ride across the countryside to deliver a message? The answer is no. This scribe also has a great job way at the top. The scribe has somebody who works for him, and that's the translator. Now, this translator does a few things for a living. He gets the message, so he takes everything the scribe put on paper, he takes it, and then he makes sure it's presentable appropriately for the far side. What do you mean, Keith, it's presentable? Well, let's say that Kingdom A, they spoke a certain dialect of language, and Kingdom B spoke a slightly different version or dialect of the language. The translator could make some changes or translations to make sure the data was presentable in a format that the other side would recognize. So in addition to correctly formatting the message, maybe adding some things that are specific to the dialect of the far side, he also may encrypt it. Now, why? Why would we encrypt a message? And what is encryption? Well, encrypting is when we take data, like this message the king is sending, and we scramble it up so that anybody who's looking at it, the average person, can't make sense of what it is. If we deliver an encrypted message on the far side at Kingdom B's side, the translator on that end could take a look at this encrypted data and de-encrypt it and actually unscramble it so that the King B could get his message. So the translator could do formatting of the message and possibly encryption, but that's his job. Now, what does and he also adds his 2 cents. So I'm using 2 cents. In the U.S., we have pennies, and a cent is an or another way of saying a penny. So the translator is going to add his 2 cents, maybe for doing compression or encryption, and then he hands it down to the next logical person in Kingdom A, and that is the lawyer. You might ask yourself, what does the lawyer, why does he have to get involved? Well, maybe we're not on good speaking terms from a kingdom perspective with Kingdom B. So the lawyer is going to negotiate the conversation. First of all, saying, is it okay to happen? If so, yes, great. I'll go ahead and let this conversation happen between King A and King B. He'll also track it. So maybe he'll do paperwork for the message being sent out and saying, oh, this is paperwork 5249. It's going to King B, etc. So he basically sets up the deal, allows this conversation to start, and keeps track of it. So that's what the lawyer does for a living. He sets up the deal. Now, here's where I like to pause just for a moment and point out that everywhere in Kingdom A, from this line up, this is really the senior management team for King A. That's the people who make the policy, they decide what's going to happen, but the actual real heavy lifting begins at the middle manager, which we're going to look at next, on the way down. So the lawyer, after agreeing to have this message being sent from the king, he's added his 2 cents to the deal as well. Again, 2 cents meaning he's just added a little bit of overhead to the message. The overhead might be the tracking number for the documents and so forth. He then hands it down to the middle manager. Now, this middle manager's job is to make sure that this message gets delivered. Now, the middle manager has a couple of options. He can choose to use reliable or unreliable delivery. Now, what does that mean, Keith? Unreliable or reliable? Well, let's think about sending a piece of mail somewhere in the country or the world. If we send a letter, so I've got a letter right here, and it says to and from right here, and I've got a stamp. If I send a letter, I could send it registered mail. And if we send this letter registered mail, it means that when it gets delivered, we'll get a confirmation acknowledgement back saying, hey, this letter was delivered. Does it cost more? Yes, it does cost more. And in the Kingdom A, if we use reliable messaging, it's going to cost a little more in overhead because we're going to track it. Maybe I put a tracking number of track number 1026. So he has a tracking number on it, and if he sends it out, the middle manager will be expecting an acknowledgement coming back from Kingdom B saying, yep, I got that message, the tracking number 1026, it got received, thank you very much. So that's what reliable is all about. It's about sending sequence numbers, tracking numbers, and getting acknowledgments back. Well, how about unreliable? This is great. Unreliable says, where the middle manager says, sure, I'll send it out, but I'm not going to ask for a receipt. It's like sending a postcard, where if it gets there, great. If it doesn't get there, great. You don't get any acknowledgement back from the delivery company talking about whether or not the postcard was delivered or not. You just hope for the best. And that's what unreliable is all about. So the middle manager is going to use reliable or unreliable transport requirements, and he is not going to just make up his own mind. He's going to do it based on a set of standards that are in place. For example, maybe if it's a message from the king, maybe the middle manager always has to use reliable. If it's some other type of message from some other person, perhaps he chooses unreliable. The other thing that happens that's really cool at the middle manager is as this message comes down from the king, maybe it's getting so big that the middle manager is going to chunk it up. Now, chunk, what does that mean? It means to carve up. So if the message is, let's say this is the entire length of the message right here. So that's the message. Now, this message isn't just the king's invitation. Remember, this message also involves the scribe's added information, the translator's added information, the lawyer added his information, and the middle manager adding the tracking. So maybe if we want to cut the message up into 2 pieces, in fact, let's use 3 pieces. So if we carve it up into 3 pieces, this middle manager might say this is 1 of 3, 2 of 3, 3 of 3, and also might have separate tracking numbers for each one. So we could track this one as, maybe 1026, and this would be another number. So he can track it. So we're taking this message and we're segmenting it into smaller chunks if needed. If that happens, the middle manager is all over it. It's really easy for him to do. So you with me so far? We have the King A who sent a message and the scribe wrote it down. The translator possibly encrypted it, massaged the data to make it presentable for the other side. The attorney, the lawyer, negotiated the conversation, maybe wrote up the documents for it, gave it a number and so forth to keep track of it. And the middle manager is now going to use reliable or unreliable transportation mechanisms and send this on its way. Now, if you look at this middle manager, he also does not have to get on his horse. Are you with me here? He doesn't have to get on his horse and ride across the countryside because there's some additional people in this stack of protocol that work for the manager. And that next person is the mailroom. Now, what does the mailroom possibly have to do with any of this? Well, the mailroom is going to add labels to the messages. And why do I say messages? Well, if the initial message was, "Dear Mr. King B, do you want to have lunch?" And if the middle manager chunked it into 1, 2, and 3 parts, each of those parts needs to have an address. Now, Keith, what do you mean address? Well, let's think about where we live for a moment. No matter where on the earth you live, if you're looking at this video and you're watching it, your home, your apartment, your condo, the dwelling in which you live has an address, and it's got 2 major parts. There's going to be a street name, and that street name is common with everybody else who lives on your street, and then you're going to have a house number. In addition, you may have an apartment number to further identify exactly which building or which unit you're in inside of a building. So just like in the example of mail here, Kingdom B and the king also has a street name that says street. Street. Let me actually just fix that real quick. So the mailroom, what they're going to do is they're going to add a label to each of these pieces of information, each parts of the message, and the label is going to be the destination address of the king, King B. So in the to field, it'll say to King B's street and to the specific house or castle number where King B lives. Also, it's going to have a from field. So this is coming from King A, who lives at this street, who lives at this specific house or castle number on that street. So that's what the mailroom does. Whenever you see the concept of logical address, I want you to think that's nothing more than a street name and a house number, just like we use today on the places where we live. Now, it's not over yet. This mailroom, once it adds that information, the destination and source addresses, the house numbers and street names, it then focuses on a particular problem, and that's the envelope stuffer. Now, what do you suppose an envelope stuffer does for a living? Well, an envelope stuffer is going to take the message and stick it in an envelope. So if we have three pieces that we have received from the middle manager that went to the mailroom and now at the envelope stuffer, those will be put into three separate envelopes. And the other challenge we have is this thing right here. Now, this may not be common for all of you, so I'm going to explain what that is. I live in Las Vegas, Nevada, and on my street, the mailman doesn't deliver directly to my house. I have a house. I have a place where I live. I've got a street. I've got a house number, but the mailman doesn't deliver directly to my house. On my street, there's a box that looks like this one. And on that box, it's got slots. There's like 1, 2, 3, 4, 5, 6, and so forth. And every house, for example, my slot number is something, and my neighbor's slot number is something different. So the mailman just puts our mail into the correct slot, and then we go collect it whenever we feel like it, hopefully fairly regularly. So that's how it works. Well, what has this got to do with Kingdom A and Kingdom B? Well, the envelope stuffer not only has to put the information into the correct envelopes, for example, UPS or FedEx or what have you, but he also needs to put the correct box number. The box number is called a physical address, and the box number is simply the ability to, the information for exactly where this should be delivered. So I just cleaned up a little bit of my space here so we can see the responsibilities of the envelope stuffer. So he's adding a label that's putting on the physical address. And whenever you see physical address, I want you to just think of the actual box number, so that once it makes it over to Kingdom B, it can be put into the correct box so that Kingdom B's people can open that box and continue looking at the message. So the mailroom has the logical addresses, which are street names and house numbers, and the envelope stuffer is going to add the physical addresses, which is like the box numbers, and it's going to put the messages in the correct envelopes. And then finally, we actually get to deliver them. Woohoo! So once we have all that information done, we have the envelopes and we have the addresses, the physical addresses and the logical addresses, then the delivery takes it over. Now, I have a truck here, and maybe it's a 21st century castle scenario, but whatever delivery mechanism we want to use, it could be a truck, it could be a car, it could be a person on a horse. They're going to take that message, those messages, and deliver them to Kingdom B's side. So what I'd like to do is have you with me imagine what happens over here at Kingdom B's side. So the message gets delivered at Kingdom B. So I'll just write that this is King B's countryside here. And what happens? The person in the truck, do they get out of the truck and go straight to the king and hand it to him? No. The entire process that we just described happens in reverse. What do you mean, Keith, in reverse? Well, the truck is going to show up and it's going to deliver the message. And the first thing that's going to happen is King B's side of the house is going to make sure that it's in their slot first. So they're going to look at their mailbox slot and look for mail. So this is the envelope checker, if you want. ENVELOPE. So they look at the envelope to verify that it's addressed to the correct mailbox number. If that's the case, they remove that. They no longer need the information regarding the mailbox, and they hand it up to the mailroom at King B's side. In the mailroom, what are they going to do? Well, wait, Keith, I think I get this. If King A added a label with the street and house number, I imagine in the mailroom on King B's side, they're going to verify that address, the street and house number, is correct for them. And that's exactly what they do. So the mailroom in King B's kingdom they look at that information and say, oh my goodness, this is our street, this is our castle number, our house number, it's for us. They remove that information because it's no longer relevant, and they pass it up. Who do they pass it up to? They pass it up to the middle manager. Again, everything that happened going down on this side is going to happen in the reverse order going up at the recipient. So here we have the middle manager. Now, what is the middle manager going to do? Well, he sees that there's a message that came in, and if it's reliable transportation, he receives it. He's going to send an acknowledgement back to Kingdom A's middle manager just to let them know, hey, Charlie, I got it. Thank you very, very much. Appreciate you sending that. Once the middle manager receives that and sends the acknowledgement, he's going to remove, for example, any tracking numbers that were on it and just send the raw message up the stack, if you will. Now, who gets it? Well, the lawyer is next. So this lawyer, the attorney, is going to take it and say, are we on good speaking terms with King A? Do I want to even let the king see this? And if the answer is yes, we're on good speaking terms, we're expecting that type of message to come in, we're willing to receive it, the lawyer is going to remove anything that the lawyer on the sending side put on, and he's going to forward the raw message going up. Now, what is this raw message? The raw message eventually is going to say, King B, do you want to have lunch? It goes to the translator. If there's any kind of formatting that needs to be done or encryption, the translator will go ahead and do that job on the receiving side. Once he does his magic, he then hands it up to the scribe on the receiving side. And the scribe will simply take the message and read it to the king as a service to King B. Now, once King B gets the invitation saying, King A would like to know if you'd like to have lunch, says the scribe. If King B wants to respond, you know what has to happen? The same thing in the reverse order. Now, why would I share this story with you? This is a logical representation of what goes on in the mind of a network device, like a computer, your PC that's sitting on a network, the thoughts that it goes through when it's getting ready to communicate on a network. I would like you to take a moment and jot down each of these roles. And if we take a look at the king, if we count starting from the bottom, we've got at the very bottom, we've got the physical, the truck driver. The envelope stuffer would be 2. The mailroom would be 3. The manager would be 4. The lawyer setting up the deal would be 5. The translator and security guy would be 6. And the scribe would be 7. And the king is the king. So I'd like you to jot that out. Take a moment right now and jot down all the roles of those layers, if you will. And once you've done that, come back and we'll continue discussing exactly what's really going on here. And here's just one more clear view of each of the roles, their titles, and what they do. So let's put all of this in perspective. If we have a computer, and let's just draw a little happy computer. He's happy because he's on a network. So he's on a network and he's talking to a bigger computer that's sharing files. So we'll call this a file server. A server that has file services available. This computer, when it wants to talk to that file server, it's going to go logically through all of these steps that we've just described. And now what I'd like to do is give you the OSI reference model step by step. Now, what you've already done, if you're participating here, is you've written down each of the roles, like the scribe and the translator and the lawyer and everything else. You've written those out step by step, including what they do, And now I'd like to ask you to write out what the OSI reference model is describing. The OSI reference model is simply a way to get our brains around the concept of what this computer is doing when it talks on the network. And I want to share with you something else. Everything in this logical model that we're going to do, all the way down to this line, that all happens logically inside the computer. Only the physical layer is where we start sending out the bits across the actual network wire itself. So let's start at the top and make sure we're comfortable with each of the pieces. Who is the king? Let's start with that. Who is the king in this role? Well, the king could be, for example, a user who's sitting at this computer who's using a word processor or some other type of program and is about to try to save some information over on a file server. So the king represents the end user or the end application that's going to be using a service like a file service. So the user sits here, they click on save, we want to save it to a hard drive that's on this file server. So the way this all starts is that the application layer is making those services available. So there's lots of different services that we can make available. We can make file services or print services for a shared printer, or maybe messaging services like the king was doing with instant messenger or email. Those are all examples of various types of services. And logically, it's the application layer that makes those network services available to the end station so that we can actually use a network resource. So I'd like you to jot down application layer, and that's level 7 in the OSI model. So if you ever hear somebody talking about, oh, this is a layer 7 device, that's what they're talking about. It's some type of device that's providing network services could be considered a layer 7 device. The application layer, after it does its presenting of services to the end device, then hands down to the presentation layer. And what does the presentation layer do for a living? Now this is where our story becomes very important. That presentation layer is responsible for what? Do you remember? What does it do? Now if you have it written down, that's awesome. If you need to go back and review, that's okay too. But the presentation layer is responsible for the formatting of data to make sure it's presentable to the other side. It also could be involved with things like compressing data and also encrypting data, and there's some other logical functions as well. But the primary job is the formatting of data to make it presentable to the king bee in our scenario. The presentation layer hands it down to the lawyer. That's the next logical step in our OSI protocol stack or OSI model. What does the session layer do? And again, I'd like you to jot out the session layer along with its number. Well, Keith, you said that the session layer, like the lawyer, sets up the deal, negotiates it, makes it happen, it's going to track it. That's exactly what happens in the OSI reference model perspective as well. The session layer is going to say, are we willing to talk to the other party? Yes or no? And if so, we're going to go ahead and track it. So it has the ability to use numbers, we call them port numbers, that are set up to track individual conversations, because in the real world, you could have one computer that's talking to a file server, it could be talking to a web server, it could be talking to another web server at the same time with 2 browser windows. So we have to track all of that. And it's the session layer in the OSI reference model that's logically responsible for negotiating and managing all those sessions and keeping them straight. So when the data comes back, we know who it came from and we can feed it to the right program or the right window on the browser. Okay, so that's the senior management team right there. Now, who actually gets the work done? That's when we go down to the transport layer. The transport layer, what does he do for a living? Well, in our analogy, The transport layer was responsible for a couple of things. Do you remember what they were? Transport layer, which is our middle manager. What does he do? Okay, good. He's responsible for things such as determining what type of transportation to use to deliver this message. Should we use reliable or unreliable? In the reliable world, we have a protocol, a primary protocol in the TCP/IP protocol suite called TCP. It's called Transmission Control Protocol, and it's reliable. What's the negative of that? It's got more overhead. We got to send acknowledgments and sequence numbers, but it is reliable. The other side of the house, put a double bar here, would be UDP, and that's a protocol, user datagram protocol. And I'll fix that. UDP, user datagram protocol, and that's an example of an unreliable transport layer protocol. UDP, if chosen to be used, will simply send the information and won't even ask for an acknowledgement. It just hopes it gets there. If it doesn't, there's no way it knows. It's just going to forward it and forget it. So this the transport layer chooses the transport type, reliable or unreliable. TCP and UDP are examples of two of those categories. And it also might segment the data. If we have a really large chunk of data, a message that's coming down, the transport layer might chunk them up into smaller segments. For example, segment 1 of 3 and 2 of 3 and 3 of 3, and it'll track all of those, and all of that work is transparent. The session layer has no idea that the transport layer is doing all this work to carve up the message into smaller pieces if needed. Why? Because the transport layer on the receiving side in Kingdom B will do the reassembling of all those segments before it hands it up to the attorney or the lawyer at the session layer. So whatever's done on one side, for example, Kingdom A, the transport layer, the far side where this message is going, is going to undo or reverse that process to make it all transparent to the levels above it. Great, you're doing great. Hang in there. Well, once it does its magic of the cutting up, the segmenting, and the reliable or unreliable transport, it then hands it down to the mailroom. And in the mailroom is called in the OSI model the network layer. So that's layer 3. And this, my friends, you're going to hear a lot. Oh, that's a layer 3 device. What does that mean? That's a device that works primarily with, guess what? Those logical addresses. Now, I told you that whenever you see the word logical address, I want you to think of like a street name and a house number. That's an example of a logical address. Well, in the world we live in, we use IP at this level, and we use IP addresses. And IP addresses are nothing more than a street name where a computer lives and the actual house number or host address of that device on that street. So at layer 3, we're going to be adding information that includes the IP address for the message that needs to be sent to its final destination. That's the primary purpose of the network layer in the OSI reference model. And again, it's just a reference. This is not a literal model of what's literally happening, but it's a good reference point for discussing it. So if somebody says, oh, gee, I've got a device on the network that looks at IP addresses and then makes forwarding decisions based on those IP addresses, that would be a router. And that's what routers do for a living. In fact, that's why routers are considered to work at layer 3 of the OSI reference model, because primarily they're receiving a packet that comes in, they're looking at the IP address like a mailman would, and then making a forwarding decision towards its final destination to move that packet on its way. And it's a layer 3 device. So that's really important as the terms come into play with, what layer it works at. because this can be used all the time in our discussions. So the network layer hands it down to the envelope stuffer. The envelope stuffer is called the Datalink Layer. And there's going to be a further discussion that we'll have about breaking the Datalink Layer down into two components. But effectively, the Datalink Layer has two responsibilities. One is, what frame, what envelope do I put it in? Which in the networking world, we call it a frame. It's a collection of data that fits in a correctly organized fashion for the media. Now, what frame type should we use? Well, if we're sending a letter, should you use a FedEx envelope or a UPS envelope or something else? And the answer is, if we're sending a letter, you'd want to use an envelope appropriate for the type of carrier that you're going to be using. So the same thing happens here. The data link layer at layer 2 of the OSI model is going to be responsible for using the correct envelope or frame type to put the information in. And a frame is nothing more than the organization of data in a certain fashion that two devices understand and accept. For example, let's say I have two PCs. There's PC 1 and there's PC 2. They're both happy. They both want to talk. How could we do it? Well, at layer 2, if we organize the data into, let's call it the KB frame, for Keith Barker, I'm just making it up. If this one sends it in a format called the KB frame, and this guy receives it and understands the KB frame, guess what? No problem. So the big deal about layer 2 is that you have to have compatible, understandable frame types, envelope types at both ends. The other piece that's a big one on the envelope stuffer is that we need to put the right box number on it. Now that box number is called a physical address. And that physical address happens to be, we use the box analogy for our street. Every computer on the network has a physical address. It's burned in to the network interface card that every computer and every device on the network has. So this physical address needs to be included in the layer 2 information so we can deliver to the right computer. So if I have 3 computers here, and computer 1 wants to forward a frame to computer 2, it needs to include the layer 2 information of what the hardware address is for computer 2. Otherwise, we'd have to forward that frame, make everybody look at it, and then PC 3 might have to look at it and waste his time. So we use intelligent forwarding based on layer 2 addresses. And then at the very bottom, we have the physical layer. And the physical layer, and this is so funny that everything above here happens logically inside the mind of a computer or network device. It's only the physical layer where we're actually sending out the actual data. The physical layer includes things like bits. Let's talk about bits for a second. A bit is like a light switch. It's on or off. So when we send information, the bit can be 1 or a 0. And we're sending those all across the network. And so as we take a look at the physical layer, how do we represent a bit? Meaning it's on or off. So on would be a 1 like this, and off would be a 0 like that. Well, there's lots of different ways of doing that. We can do it on copper wires by changing the voltages to represent 1s or 0s. We can do it on wireless by changing the radio frequency to represent 1s or 0s, or changing the encoding on that radio frequency. And we can even do it with light, with fiber optics representing 1s or 0s. But whenever you think about the physical layer, I want you to think of Morse code. Let's talk about Morse code for a moment. Keith, Morse code. What do you mean Morse code? Well, when I was in Scouts, when I was a younger person, I learned some basic things about Morse code. Now, Morse code is represented by dots and dashes, and you have the whole alphabet. But I learned two letters, S, which is dot, 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 and O, which is dash, dash, dash. So if I wanted to communicate this to somebody, I could say dot, 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 dash, 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 and they would say, oh, that's SO. How's that help? Well, the reason I learned it in Scouts was because I could do an S again, dot, 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 and I could communicate SOS in Morse code. When you think about computer networks and one computer talking to another, I want you to think about Morse code. Because when we send data from one PC to another on the physical medium, which doesn't have to be tangible, it could be radio frequency, airwaves, the actual information that's being sent is just a collection of ones and zeros. So sort of like Morse code, and you have sending millions of ones and zeros, but they're all sent, pretty much one at a time across the network. So as one device sends the ones and zeros, some other device on the network is picking those ones and zeros up and analyzing what they are, making sure those ones and zeros are for the correct device, and then moving it up the protocol stack. So in the OSI reference model, here's an important concept. I'm going to clear this up a little bit, and let's do a couple review pieces. When data is being sent down the protocol stack to 7, to 6, to 5, to level 4, 3, 2, and 1, when it's being sent down, they call that process encapsulation. And why is that important? Because encapsulation is a term that's happening all the time on computer networks because we're either encapsulating data, that means taking everything that the session layer gave us and the transport layer encapsulates that and adds its 2 cents, remember? And the network layer takes everything that the transport layer gave it and adds its 2 cents. And that process is called encapsulation. And the message itself is getting slightly bigger each time, but the ability to take what was given you, encapsulate it, and then send it down the protocol stack further is a process called encapsulation. Now, when this data, these ones and zeros, are received at King B's side, and they move it up the protocol stack, you know what that's called? You guessed it. That's called de-encapsulation. So those are two terms you're going to hear all the time. Encapsulation is where you're taking data and you're taking everything that was given you, adding your 2 cents, and passing it down the protocol stack. And de-encapsulation is taking what you receive, stripping off that level of information, and moving it up the protocol stack. So what have we learned so far? Well, we've covered a cool story about King A and King B. We've learned some roles of the scribe and translator and the lawyer. We've also learned their official names in the OSI reference model, which you should prepare yourselves to have committed to memory. Now, one of the things that I like to do is I like to use mnemonics from time to time. Mnemonics, what does that mean? It's where you take a phrase that helps remember something else. For example, if I said, please don't, let's use a different one. That's not too cool. Well, let's do this. How about please do not throw sausage pizza away? Let's go with that. There's a couple other variants on that, but that's pretty safe. So if I could remember that phrase completely, please do not throw sausage pizza away, or please do not take salesperson's advice, or some other mnemonic that helped me remember, I would then know each of the names of these layers, and I could recall them just by remembering my mnemonic. So I just took the first letter from each one and made a mnemonic, and that's one way of remembering it. Also, it's important to know that like professional bricklayers, we start from the ground up and we work our way up. As far as the levels go. So encapsulation is where we take data and it goes down the protocol stack, and de-encapsulation is where we take the data and strip off the headers, the information that was added by the other side as we move the data up the protocol stack. So we've talked about the story of King A and King B. We've talked about the layers of the OSI reference model, and we know what they do. And I also just want to add one other key thing is that when each of these layers do add their own 2 cents, their information to the message, it's added with something called a header. It's a little tag on with their information. For example, the network layer in the header, it's adding information such as the IP address. At the Datalink layer, it's adding information such as the mailbox number, also called the physical address of the network adapters involved. So the headers are where we add that information. So what else do we need to talk about? Well, I've got some great news for you. You definitely want to have the 7 layers of the OSI reference model committed to memory, but we don't use for our most of the networks that you and I are customers on, we don't use the OSI model. It's just a reference point for describing the logic of what that PC does in its mind as it's working on the network. In reality, we use something called the TCP/IP protocol suite. And a lot of people ask, okay, Keith, how did that happen? Well, the internet has not been around forever. Are you with me? It hasn't been around indefinitely. It was started by a group of folks, a group of people who were building networks. And when they were creating these networks, there was the International Standards Organization, that's the ISO, gotta love that one, who made the OSI model, but there was also another group called the IETF, the Internet Engineering Task Force, the IETF, who were working on TCP/IP. Now, possession is 9/10 of the law. And on these networks that were being developed and used, the IETF was using their TCP/IP implementation. And my friends, that's why the internet is running TCP/IP protocol stack today, is because it was in use, it was in place, and no one wanted to go and implement some type of OSI protocol stack. So for all intents and purposes, we don't use the OSI protocol stack. There are some protocols out there on the edge, like ISIS, that do conform to this a little bit, but for 99.9% of all our production networks, we're using the TCP/IP protocol suite. Now, good news. There's not 7 layers in the TCP/IP protocol suite. In fact, there is 4. If we take these 3 right here, layers 5, 6, and 7, that corresponds to the application layer of the TCP/IP protocol suite. You know what that means to you and me? That means anything that happened at layers 5, 6, or 7, logically, things like providing network services, modifying the data to make it presentable to the other side, or encryption, or the compression of data, the session layer like the attorney setting up the deal, all of that information gets lumped into the application layer of the TCP/IP protocol suite. One level does it all. It's just all boiled together. And the reality is, because this is happening all logically inside of a computer or a server, we really can't see it anyway. So in TCP/IP, it's all one lump. The transport layer is a one-to-one translation, meaning the transport layer in the OSI model matches exactly what the transport layer does in the TCP/IP protocol suite. Now, my question for you is, do you remember what the transport layer does? Layer 4 of the OSI model What does it do? And I'll wait for you. Your turn. What does it do? Now, maybe you're thinking to yourself, oh, I've got it down pat, no problem. And maybe you're thinking, I'm going to go over this module, this nugget a couple more times. Either way is perfectly acceptable. I want to make sure you get it. The transport layer is responsible for deciding the type of transport to use, reliable or unreliable. And it also, if we had a large message, could be responsible for chunking that larger message into smaller chunks. So that's the primary responsibility of the transport layer, is choosing the transport, reliable or unreliable, and then identifying each of the chunks if it's going to chunk it up into smaller pieces. All right, so transport layer comes across straight over, and the network layer comes across straight over. Isn't that great? Except they don't call it the network layer in the TCP/IP protocol suite. They call it the internet layer. So if you're talking with friends and you're talking about the TCP/IP protocol suite and you say network layer, no one is going to bat an eye because you, like me, know what it means. So the network layer and internet layer, synonymous. Now where it gets a little bit dicey is this one right here. The Datalink layer and the physical layer from the OSI model get lumped into something called the network interface layer. So anything that has to do with physical signals like electrons or radio frequencies sending bits across the wire, or physical cables that connect for our networks, also anything that layer 2, for example MAC addresses and things like that, they all get lumped into this level right here. Now, I just mentioned MAC addresses. I should point out what that is. On this computer, it has a network interface card, and that network interface card, sometimes the acronym for that is Network Interface Card, like NIC. That network interface card has a burned-in physical address, and that physical address is called a MAC, not as in Apple, but capital M, capital A, capital C, for Media Access Control. So if you ever see MAC address or physical address, they're talking about that burned-in address that every network interface card has on every computer on the network. So that's what that refers to. So it's bundled into two. So there's our 4 layers of the TCP/IP protocol suite, and that's pretty straightforward. But check this out, one more little twist. When we're talking about networks, we don't literally use the OSI model, nor do we use the TCP/IP model. We kind of use a hybrid, and I'll put it in a different color. So here's what we do. For the physical, when we talk about the networks in general, if we say somebody's talking about level or layer 1, that's going to be physical. And that's whether we're using the TCP/IP protocol suite or anything else, it's basically the physical. And 2 is going to be data link. So if somebody said, oh, we're working with TCP/IP and we're working with a layer 2 device, a layer 2 device is some device that's working with or making decisions on layer 2 addresses, such as a MAC address is a perfect example of a layer 2 address. A device in our computer networks today that does that exactly is a switch. A switch is a layer 2 device. We'll have another discussion on switches coming up, but a switch is an example of a layer 2 device. At layer 3, the network layer, and the primary device there would be a router. That's because a router makes decisions based on layer 3 addresses, making forwarding decisions. So a switch operating at layer 2 or a router operating at layer 3, that's why they're referred to as layer 2 or layer 3 devices. And layer 4 is the transport layer. So even though we don't literally use the OSI reference model, we use TCP/IP instead. But when we're referring to levels 1, 2, 3, and 4, it's referring to the OSI reference models 1, 2, 3, and 4, even if we're using TCP/IP, which doesn't match up exactly. And then the application layer, we don't actually call that layer 5. We just call it the application layer, which, as we now know, includes everything from those functions of layers 5, 6, and 7. So on our networks today, we have TCP/IP as the primary protocol. There's two flavors. There's TCP/IP version 4 and TCP/IP version 6. And there's similarities and differences between those two. But the concept here I want to drive home is that when we're referring to our networks and how they operate, layer 1 is physical, 2 is data link, 3 is network, 4 is transport, layer 5 is application layer, even though we're using TCP/IP. So now that we have an understanding of the OSI reference model and the TCP/IP protocol suite, let's apply what we now know to real traffic. So we're going to take a computer. So here's a happy computer sitting right there. He's on the network. He's like, you know why he's excited? He's excited because he gets to go out to the internet. Woohoo! And then we've got this device that's a router. And I'll put an R for router that's connected to the internet. I know the internet looks a lot bigger on TV, but let's say this is the internet for now. And out there we've got various servers and the rest of the world all sitting on the internet. Big I for internet. So we'll bring in a PC, and I'm going to do something extremely cool, and I want to prepare you for that. I'm going to put what's called a traffic analyzer, a protocol analyzer on the network right here that's looking at every single bit that my computer spits out on the network. Now, behind the scenes, because we're running the TCP/IP protocol suite, we'll have the application layer that'll be encapsulated by the transport layer, and then the internet layer, and then it'll go down to the network interface layer, which is the data link and physical, and be spit out. But the protocol analyzer will be able to capture all of that so we can actually see in real terms that it's really happening. So let me start my protocol analyzer in the background here. So it is capturing as we speak right now. I'll keep this all real time. We'll bring in the PC. We'll open up a browser. We'll go to Internet Explorer because it's handy, and we'll go to google.com. And there it is. So here's the protocol analyzer that's showing us the details of this fairly busy network. And let me bring up a little bit. And I'm going to give you a little heads up scoop as to why it took a little longer for that to work than previously. See, my computer right here, as smart as it is, when I typed in www.google.com, it said, I don't know what the address is of google.com, the layer 3 logical IP address. And so what it did, it actually made a request out to a server called a DNS, Domain Name System Server, and it said, I have a need. I need to look up an IP address. I need to know what the IP address is for www.google.com. That reply comes back, and then that PC uses that IP address to forward packets to google.com. So here's actually, wow, look at this. This explains why it took a little longer than normal. Here we have a request. This DNS request that was initially made is my computer at this IP address asking its DNS server about how to reach google.com. And 4 A's represents an IPv6 address, which my client, the PC I'm on, is not running. So basically it got a response back saying, yeah, your server's at this IPv6 address. Since my PC isn't running IPv6, it made another request for an A record. An A record is a standard IP version 4 address saying, I need to know the IPv4 address for google.com. The response came back, oh, he's at this IP address. And it's after that that my client can then go ahead and make a request. It looks like I did a few more queries. It looked like I had a malformed packet, and that would explain why it took a few additional moments for it to figure out what the IP address was and then send out the request. All right, so once it made the request and found the IP address of the server, it did a few additional things, but here's what I want to focus on. This is our PC, the one we were just sitting at, that's actually communicating out with the server. And in this protocol analyzer, it has them in order, if you will. So level 1 is up here. Let me write those out real quick. So from an OSI reference model perspective, this would be layer 1 or level 1. This would be level 2 and level 3 and level 4. And here we have the application layer. Remember how I talked about we use kind of a combination of the OSI for the bottom 4, and then we use just call the top 3, 5, 6, and 7. We call it the application layer. Let's take a look and see what's inside each one of those. So at the application layer, again, this would be a service that we're providing for the king or for the end application. The application in this case would be our Internet Explorer that was requesting services. What kind of services? It was requesting HTTP services, which stands for Hypertext Transfer Protocol, which is the language of love between a PC or a device and a web server. So this is all application layer stuff right here. If we go down one level in the protocol stack to level 4, we would be looking at the transport layer. Now, the transport layer has 2 major protocols that we introduced earlier. And those 2 major protocols are TCP and UDP. TCP was connection-oriented and reliable, and UDP is connection-less and unreliable. So which one did we use here at the transport layer? Well, we used TCP, Transmission Control Protocol. And because it's reliable, TCP uses the overhead of sending sequence numbers and acknowledgments. And so that's all in this header. In fact, everything that's been added in this data right here in the TCP header is all about the actual tracking. So we have the sequence numbers and some acknowledgement numbers. It also is keeping track of something called port numbers, which we'll get into more detail on. But when the session layer set up the deal, the lawyer, he assigned logical numbers, port numbers, to track this session. And so in the TCP header, it's also keeping track of those session numbers so it can make sure that the right data gets to the right application. So this is an example of layer 4 of the OSI reference model. This is the header adding on the information regarding the sequencing and the tracking of that piece of information. As we go up, or I should go say down one more layer to the network layer, we've got the internet layer or the network layer, depending on which one you want to call it. So here, the network layer. Remember what layer that is? It is 3. Good job. And at the network layer, this is the 2 cents, if you will, that's added by the network layer. And again, this is all logical because it's all done inside of the head of the computer. But the IP header inside of IP packets, the primary thing that we're focused on here is adding the source address. That's an example of our IP address, like the street and house number where we live, and the destination IP address, which is the street name and house number for the destination of this packet. In this case, that destination is our Google server. So that's layer 3 of the OSI reference model. And if we go down one more to layer 2, here's our layer 2 information. And this is the data link. You remember what gets added at the Datalink layer? In the header of the Datalink layer is where we're going to add the information that's required. And that information is the mailbox numbers, the physical address. these are examples right here of physical addresses. So this is the PC that we're sitting at, and this is the MAC address, the physical layer 2 address of our default gateway. And that's a new term. And I've got a little confession to make. Are you ready? Here's my confession. My computer is not sitting on the same exact network as google.com. My computer is here in my office, and google.com is somewhere out there on the internet. So when I want to communicate with some device that's not local to me, like a Google server that's far, far away, when I forward my data at layer 2, I'm going to have my MAC address as the source, and the destination is going to be the MAC address, the physical address of my router. That way it can get delivered to the router directly. He can look at the IP address and say, okay, I've got this packet, it's not for me, and he can make his forwarding decision on that packet towards the internet. So this is layer 2 of the OSI model. And if we go down to layer 1, it doesn't get too exciting. This is all the details about the actual bits itself. So we know that there's 4,368 bits total that were collected, which works out to about 546 bytes, and that's it. So what have we learned in this lesson? Well, let's just take a look. We've learned that logically we can forward data down a protocol stack, and that process is called encapsulation. Every piece has the opportunity to add its own 2 cents. What we just witnessed is that at the transport layer, it added things such as sequence numbers. There was also port numbers in the header at layer 4. The network layer, it added header, and that header information had primarily the IP addresses, which are the logical addresses, the street names and house numbers of where this packet is coming from and where it's going to. At the Datalink layer, it added the physical addresses, which is like the mailbox slot numbers. And then the physical layer right here, it just simply spit out the bits and they went across. There's another tip that's really important that I'd like to share with you right now. And that is, we have special names for the message or for data as it goes down a protocol stack. And that data is often referred to as a PDU, a protocol data unit. So one day somebody said, well, what do you call the message as it's being sent from the keying, or in this case our HTTP request to a web page? What do you call it when layer 4 adds a header to it? Or what do you call it after layer 3 adds a header to it? Or what do you call it when layer 2 adds a header to it? And the answer was determined to be, why don't we give these guys names so that we can be clear when we're talking with each other. And that's the primary benefit of it. At the transport layer, when the message comes down, in this case was our HTTP request, when it hits the transport layer and it adds its header with the sequence numbers and so forth, they call the data at that layer, they call it a segment. What do you mean, Keith, a segment? A segment of data. And that's a pretty good term for it, because if we get a large request or a large file and we're going to chop it up into smaller chunks, we're going to segment, if you will, that data into smaller chunks. And each segment is going to have the information for tracking that from the transport layer. So this is the name of the PDU, the protocol data unit, once we have an IPv4 or a layer 4 header on it. Once that information gets handed down to IP, to the internet layer, it's going to go ahead and add its header, and at that moment we can call it a packet. Now, that's a term that we've heard all the time. I know it. So people say, oh yeah, there's a packet going across the network. And if somebody comes up and says, oh, a packet's going across the network or a packet was sent, they're just generally referring to data that's moving. But you and I, now that we know, we can accurately call a packet it's data that's gone down the protocol stack and includes now IP address information. An IP header, once it's on the actual data, we can refer to that as a packet. Once that gets handed down to the Datalink layer, the envelope stuffer goes to work. We put that envelope into, or put that data into an envelope, and that organization of the data into an envelope is called a frame. A frame of data. You know, like having a frame of reference? We have a frame of data. You know what the best frame format to use is? The best rule? It's the one that two computers agree to. So today there's some really common standards for frame formats. We'll cover that in a separate lesson on media. But as long as two devices on an Ethernet network use the same type of frames, then when we send data from one device to another with the appropriate layer 2 addresses added to those frames, then the sender and receiver can both understand and process those frames because they're organized. The bits in certain orders that they're expecting to see, so they can both process that data. And then finally, once we send bits down the wire at the physical layer, we just call them bits. So what's an acronym we can use for this, or a mnemonic? Some people fear birthdays. Some people fear birthdays, if that helps. Or you can make up your own. Feel free, as long as you can remember segments, packets, frames, and bits. So when somebody's talking about bits, all we're talking about is stuff at the physical layer being moved. Ones and zeros like Morse code being sent between one device and another. If we talk about a frame of data, you and I both now know that a frame of data refers to data as it's layer 2 logically in the computer or the server, and that layer 2 data includes the source and destination physical addresses like the slot numbers on the mailbox. At layer 3, we could refer to that data as a packet. A packet simply includes the data about the IP addressing. The source IP address, which is like street name and house number, and for the source and destination, which in an IP world is the IP address. And then at the transport layer, once we've taken a look at, it has the data for the segmenting of the data and the ports involved, we could refer to that as a segment. So I would strongly recommend that you make sure that you have all 7 layers of the OSI reference model committed to memory. Remember the King A, King B story, so you remember what they do, and then also how they correspond roughly to the TCP/IP protocol suite and the names for each of those PDUs at various levels. So there you have it, my friend, the OSI reference model and TCP/IP protocol suite. Let's step back together for a moment and make sure we're comfortable with the fundamental pieces that we've covered. The OSI is pretty important because it's going to be everywhere you go in networking. It's not a literal model, but it is a model. And that brings us up to our first review point. What is the benefit? What's the reason for a model? And the answer to that is that it gives us the ability, you and I as technicians and network engineers, network designers, etc., it gives you and I the ability to identify and communicate about protocols. Protocol is nothing more than a set of rules. So now, as you get more comfortable with the concept of a frame, we could talk about frames. And if I say the word frames, you'll say, oh yeah, frames is at layer 2. And a frame is the information that includes the layer 2 header, which on Ethernet networks is the source and destination MAC addresses. So all that will become more second nature as we refer to it. We'll understand that a layer 3 device, would be a device that works primarily with IP addressing, which is what routers do for a living. They forward packets based on IP addresses. So by saying the word packet, that's a clue that we're talking about layer 3 just in the word alone. Between your friends and so forth, you don't need to correct them every time they refer to something at layer 4 as a packet instead of a segment, but you can be aware that there are terms for those PDUs, and now you know them. So defining the functions of what each layer does is also critical, using the King A and King B analogy. You can remember exactly what each level does. And you may want to go back and review that part of our discussion together a couple of times. My homework assignment for you is to find someone, either in person or over the phone, a friend, a colleague, a loved one, what have you, and I'd like you to explain the King A, King B story to them. You don't even have to tell them that it's a direct correlation to the OSI reference model of how computer networks operate. You can just tell it as a story with King A and King B, and that will rehearse or reinforce in your mind the concepts of how each layer works with the next layer for encapsulating data as it goes down the protocol stack, or the out of the receiving side de-encapsulates the data and processes it. So that's your homework. I really want you to do it. I want you to find somebody and share with them the King A, King B story, and in your own mind you can know that's the OSI reference model we're talking about. Okay, so what are the names for the data at each layer? That's my question for you right now. What are the names for the data? And you don't have to do all 7 layers. I'm just interested in layers 4, 3, 2, and 1. So what are they? I'm going to jot out some labels over here. I'll say I've got bits, got packets, I've got frames, and I've got segments. So if we're talking about the data logically at each of the levels of the OSI reference model, where do they fit? It's about this time in the presentation where people say, oh, I wish I'd remembered that mnemonic you gave us. Some people fear birthdays. You know, that would serve us well. Some people fear birthdays. That's levels 4, 3, 2, and 1. So that means bits are the currency at level 1 of the OSI reference model. Frames are the currency at level 2. A frame includes the source and destination layer 2 physical address. And we have packets at layer 3, which is a PDU, a protocol data unit that includes the source and destination IP address. And then we have segments at layer 4 of the OSI reference model, which includes the port numbers involved, the sequence numbering and acknowledgments and so forth to keep track of that segment of data. You did great. Now the last piece is, what exactly is added at each level of the OSI reference model? What is the data? What is the relevant information that's added? And we just covered it in our review a moment ago, and that is at the segment at layer 4, we have information regarding the sequencing of those segments and also the tracking of those segments. So like a tracking number, if you will. At layer 3, the information we're adding is IP addresses. At layer 2, at frames, what we're adding in the header is we're adding the source and destination layer 2 addresses, which on most of our networks, our Ethernet networks, is the MAC address, the Media Access Control address, also called, unfortunately, the physical address. But it really is a layer 2 address that every single network interface card on the planet has burned into it, and they're all unique. And the only one that we really don't have header information added to is the bits at level 1. At layer 1, we simply have ones and zeros being spit out across the medium, and that medium could be copper, it could be fiber optics with light, or it could be radio frequencies over the airwaves. And that all are valid ways of communicating those ones and zeros between two devices on a network today. Well, I have absolutely enjoyed our time together in this nugget on the OSI reference model. I hope this has been informative for you, and I'd like to thank you for viewing.